dexterity. Is that a thing? Sure. So basically we're doing chapters 13, 14, 11 is what we've covered so far. And that's like gear basics, gear stress, and bearings. These are the problems that Dr. Ghosh would usually like assign or say to tell students that this is what they should prepare for quizzes and for exams. He didn't give out homework. He just said, here's some problems, go look them up and try to work with them. And I prefer to actually come up with new assignments instead of just doing the ones that are in the book. But these are problems in the book that we should be totally able to be able to do. Although some of them are way too long to do as an exam. So I put them out there up on PowerPoint here because a lot of times I would do this on the board. I'd project this onto the whiteboard and then right on top of it. But I think it's better to use the document camera right here. We have all these, so like you could do these on your own, and I gave you the in between numbers in another document. Let me see here. So that's posted. I find that's a pretty useful way to would be to prepare to go through these. So I think in terms of the best way to spend our time is maybe to look at other problems besides the ones that are I'm already giving you the solutions for, and here's ones that you already have the answers for. All right, so this is posted right here. So what is there a particular direction or type of problem that you would like to look at? We could just go pick up some random problem and attempt to solve it if you'd like.
So I didn't really I don't think I really grasped a big understanding of the planetary gears.
Okay.
I don't know if that's going to be on the exam, but
well,
I feel like I should kind of like get a little more understanding of that.
Sure. Okay. Well, let's pick some rando. So I don't have a whole lot of those prepared, but we could do. I don't want to riff too much here. I could go a little nuts trying to think of a new problem off the top of my head. But if we go to our Blackboard page and take a look at our, we can invent a problem based on, oh, my internet connection is like slow. Look at that. Speed up. Come on. My wife isn't even on the treadmill. Treadmill downstairs in the garage messes with my internet connection up here over the garage. All right, so let's say that we're going to take one of these guys right here, just randomly, right? And we want to try to find them out, figure out the gear ratio. Let's take an L type. We haven't done an L type. Oops, I didn't mean to click on the paint. I meant to go snipper. That's okay. It's my computer has decided to go that slow to open up the paint. It's like taking forever. Look at that. That's concerning. This is making for good video. Why isn't that opening up? Did I exhaust my computer today? Here we go. Click on them again. Still nothing. There you go. Oh, 2 of them opened up. Great. All right, so I'm going to keep that over to the side and go to camera. Come on, camera. There you go. You right side up? Yeah, you're right side up. Okay. So let's take, let's say we got this hypothetical thing going on right here. So, you know, trying to look through here, figure out what's taking place. We'll say that we got a shaft inside a shaft going on. What's the best way to represent that? I'm trying to think how I've shown that before right here. So yeah, okay, so this is like a weird arm that's coming up like this right here, and I guess it's going to have like a little post coming up. Okay, and then we're going to have a gear like that right there. And then I want to draw, let's see, I guess I'll draw the shaft like that right there. Okay. And here's my inner shaft right there. That's the carrier that's taking place. And I need to make this a little longer here. Riffing on this one. We're just riffing on this one. Okay. So yeah, he's got this guy sticking out right there. I'm trying to make this even longer right there. Okay. So we got a gear that's riding on that right there. All right, and then we have another gear that's right here, and he's passing through right there. So he's on a shaft that's passing through this right in there. And now there's going to be a stationary ring. Well, it doesn't have to be stationary. All right. And so sometimes actually what I would do so probably like maybe you'd be more familiar with where I have the shaft coming out the other side right here, right? So we might have this right here, right? So this is the ring shaft is right here, and we might have the arm shaft is going to be inside this one right here, right? So that might be closer to what we're used to, but either way, right there, there we have right there, right? So this is the sun gear right here. Here's planets that are taking place, and here's a ring, right? So if we were to draw this thing, I don't have enough room really on my paper to make it to scale, but we'd have a sun, we go planet right here, we'd have a planet, and then there's a planet behind him right there, that one, they're on the same shaft. And then we have a ring, right, that this thing runs on. So it's that gear is that gear right there, and it's running on this ring. So if we want to figure out like how many teeth this could have, we could just randomly pick out some. Let's say that this one, just looking at the thing, this looks kind of big. I'm gonna say he's 40 teeth. Let's say this guy has like 20 teeth, and he looks about to be the same size. So he's 20 teeth, and this one looks like he's even bigger than him. So let's make him have 60 teeth, right? So now this outer gear can only have like, you know, if we have to use the same pitch for all of them. So the number of teeth will be like kind of very similar to you know, it will go along in the same way as the radius or the diameter or the radius, either that you want. So for here, we would say that this outside one has to have 20. Right, so I'm going by radius of the thing, right? So it would be when we get done, we're going to multiply by 2 to get what the actual number of teeth are for here. So this distance has to be the radius right there of that one, but plus the diameter of that one, plus, let's say, the radius of this one right here. What I said, I'm multiplying. I should be adding. Sorry. And the radius of this one, right, from right to there, so that's 10, plus the radius of this one, which is going to be 30. So let's see if I did that right. The radius of this one is 20. The entire diameter of that one is 20. The radius of this one, which is 10, and then the radius of this one, which is 30. And then we're going to multiply that by 2. You following what I'm the logic?
Yes.
All right. So that's 80. So my outer gear has to have 60. I mean 160. So let's number these things. And for whatever reason, we don't like to use the number 1. So this is number 2, 3, 4, 5, and this would be 6. So N2 we said was 40, N3 looked like 20, N4 was 20. So this was 2, 3, 4, 5, 6. So N5 is, which one did I say? He was the 60. And then the N6 was 180. All right, so that's like a first planetary gear task, right? Just trying to figure out the arrangement of the thing and how everybody is doing, right? We started off with this funny looking thing right here. And now we get kind of a better idea of what that would actually look like. So now we want to try to figure out the different shafts. So I'm going to call this one shaft A. I'm going to call this shaft B, and this is shaft C, like as an output of the thing. And first thing, our task we want to do probably is to figure out our gear train ratio. So that's going to be E is going to be equal to the drivers divided by the driven. So let's see. Gear 2 drives gear 3. So we'll go, I guess I'll do it by way of variables first so we know which one we're talking about. So there's N2 drives N3, N3 drives N4. N4 doesn't drive anything, right? It's just, its shaft does rotate, but 5 drives 6. And so let me get the 160 out of the way there. Okay. So we're going to say that that's going to be 40, and we could actually just kind of like ignore these two right there. So I'm just going to put the 20 in there, and the 60 here, and the 180. Now we got to decide whether this is positive or negative. That's the hard thing to do. Well, it's not really that hard. Once you've done it, like practiced a couple times, and you look at the thing and go, oh, it just kind of makes sense. You want to hold the arm as if the arm is like fixed, and then rotate the sun, and then see which way the ring turns. So let's go, just because it's easier to look at it that way for me. I'm going to go clockwise for the sun. So we have to decide if this goes clockwise or counterclockwise. So he's going to go counterclockwise. So he's going to go clockwise, right? Which means that this guy goes clockwise. And now, because this is it has inner gear teeth, it too has to go clockwise. And if you were to look over here, it makes a lot more sense, right? That you could see that guy going clockwise forces, like if there's a tooth right here and he's passing in that direction, the tooth on this one, it too has to go in that direction. Otherwise, the teeth are passing through each other. Does that make sense?
Yeah, just a question though. So the E equation, you have N2 drives N3, or gear 2 drives gear 3, gear 3 drives gear 4. and 4 and 5 are on the same shaft. Do you not put a fraction for those?
No, because whereas the shafts are turning at the same, the gears are turning at the same speed, so it doesn't do any kind of ratio.
Okay, got it.
That would be one way of phrasing it. Okay, so what we've decided is this went clockwise and that went clockwise, so this is a positive answer right here. So we can come up with our 40 times 60 divided by 20 and 160. Whoop, I just messed up something up here. I think I was thinking it was going to be 180. So I'm going to recalculate that because now I'm not sure I entered it in the right way. And I wrote 180 from right there. That's why I was about to do it. 80 plus 80 is not 180. Math. So this is interesting. It's only 0.75. That's interesting. Huh. Yeah, doesn't come out to a lot. Try it again. 0.75, Mark. So now we have like three different scenarios. Let's say that, well, for scenario number one, let's say that the ring is fixed and our input, which is the sun, is going to be 1,000 RPM. This is a good number. Scenario two is going to be that the arm is fixed and let's say the sun is 1,000 RPM. And then scenario three will make the sun is fixed. And let's make the arm, which is shaft B, is 1,000 RPM. And let's just say they're all clockwise. Why not? Is there any other scenario? Is there any other thing where at least one of them is going to be fixed at any different time? Okay. We could also have like crazy things where one of them is not fixed. Like we could have this thing having an RPM in, and this arm could have an RPM in, and then we could figure out which direction and speed the ring is going. Right. So that is possible. You could have different power sources combining together. Be quite confusing, but you could do it. It's possible. So anyway, for this right here, we use the equation, and I need to look it up because I'm going to get it wrong if I use my memory. So I got to figure out where my mouse is. Where'd you go, mouse? There you go. See, as I'm seeing it double on here on my other monitor, I can see the thing. See? Ooh, boy, computer, you're slow. It's like taking forever just for the thing to show up. Oh, that's scary. Come on, piece of junk. Well, it did get hurt last year. I heard a bloop. Is that you? We have another person here. Yay. Oh, that you just wrote the equation. Okay. Yeah, let's do it. Okay. So it's going to be the last NL minus NA. That looks right to me. Over the NF minus NA. Okay, great. Thank you. So what we do is we replace what we consider to be the first one is going to be this the sun, right? So we say for here, and the last one is the ring, but the ring is fixed, right? So we'll say 1 minus, and let's just say that clockwise is positive. Why not? We could make that choice. We don't usually do. But the arm is going to be the output here because the ring is fixed, and the sun is the input shaft right here. So the arm is C, right? And the first is the 1000, and also this one is also NC. So here's the one where you have to do a little bit of algebra to the thing, right? So you go 0.75 times 1000 minus NC is going to be equal to minus NC, right? So what do? We got 750. It's going to be equal to 0.75. Does that work? Yeah, it does. Okay. 0.75 NC minus NC, right? Did I do that right? Math is hard. So you're going to get what, negative 0.25 on that side? So we divide 750 by 0.25. So we get a negative, I can't see my thing. Doesn't seem right. A negative 3,000. I'm going to double check what I did right there. Double check my math. 750. Now we get to 0.75, but we're going to jump them over there. It's going to make it positive. So we're going to add this positive thing to this negative one. So that's going to be, yeah, should be point, yeah.
I got negative 3,000 as well.
2,000 or 3,000?
3.
Yeah,
Okay.
I got the same thing, negative 3,000.
Yeah, so that's kind of an interesting kind of result right there, right? It's a reversing. So in this configuration, it's reversing, and it's a speed increaser. So that's kind of cool. It's almost like a little mystery thing, these planetary gears. So and then, well, we could run through the other ones too, but that's the same idea right here. Now the arm is fixed, so this is usually kind of an easier one to do right here, and that's going to equal the last one, right? So the last one is the ring, right? So the ring is the output if the arm is fixed, and we have this right here. So that's going to be the last one, or we can substitute in for what it's going to be. That's going to be, I think I just said the wrong thing right here. I called it C, but that should have been B. My bad. The way I've labeled it right up above is that arm is actually B. What you get for trying to invent a problem. All kinds of hazard. Okay, so that was NB. So this one, though, now the ring is C. The ring is shaft C right here. Okay. And which is the last one, is what we call the last one. And it's minus the arm, which is fixed. And then we have the 1,000, which is our first. So that's pretty easy to do, right? Should just have 750 RPM. And this will be clockwise, whereas this one shows itself to be counterclockwise. I just didn't rewrite the thing out. And then the last scenario that we have, the sun is fixed, right? So that's going to be the first one. And the arm is going at 1,000 RPM. So we got 0.75 is going to be equal to, and we want to find out the last one, which is the ring, which is NC again. And this one is, once again, this is the first one, but it's fixed, and we got 1,000, right? So we're left with negative 750. It's going to be equal to NC minus 1,000. So NC is going to be 250. So, and that's clockwise, and then we should probably write this one out again, so we don't put the negative and the counterclockwise together. We can say that it's 3,000 RPM counterclockwise. Does that clear it up a little bit more?
Yes, that actually is pretty simple, more simple than I remember.
Yeah, if you just treat them kind of like go through the methodology onto the thing, each one, and practice it once, you'll be like, okay, yeah. What other topics? Bernard, you're please throw out something that you say, hey, I really need some help reviewing this. Here's an area where I'm confused.
So, will there be like regarding the planetary gears? Will there be a question? Will there be like a question where we involve planetary gears to the agma bending or like non-agma bending and like stresses?
I think that would be a little too cruel. Like it would be a little bit over the top. I kind of try to isolate the things. I do like the concept of merging topics together, but as a practical matter, I could just throw students off because they hadn't done that yet. But
Okay. Well,
yeah,
I was about to ask you, because if so, would our like if we were, well, if you were to do that, I was gonna ask you about the I part, the what is it? Um, wait, I'm like going through my textbook right now. I'm just trying to find where it is. So like for the I for surface strength geometry factor, um, like what's the difference between like the external gears and internal gears? Like with the like it like the external gears, it would be like the regular gears, and like the internal gear would be like the ring of the of like planetary gears, right?
yes, that's what they mean. Yep.
Okay. Yeah. I mean, you pretty much answered my question to begin with, because I was asking if you were gonna like merge topics like that.
Yeah, I kind of as in, there's philosophically, I like the idea, but then like when it starts to, as a practical matter, when trying to, I'm mostly as a when writing an exam, trying to just measure people's mastery and not trying to just trip them up. But
Yeah.
I guess in some respects, you would really know if somebody really has mastered it, if they've seen something and it's the very first time that they're seeing it, but now they have to apply the thing. So like if it was like if I taught a course that built upon the stuff we're learning here, but now just went into way more detail and trying to make sure that like, oh wow, you're going to be a master mechanical designer, I would give you that kind of question,
Hmm.
right? Just to try to see like, hey, do you really get it, right? But the problem is, if you ask a question that's like that, a lot of people aren't going to even be able to start it, and then they're just going to bomb it, and then they're going to fail the exam because they didn't answer the question at all because they had no idea how to start it.
Yeah.
Yeah. So
Um. Also, wait. The For the example problem from class 11 for problem 1125.
okay.
Yeah, I just have I'm just like a little a little confused on the part where like with the formulas. So like the one of the formulas with the bearings is the C10 times AF times FG
Yep.
times the XG with to the power of 1 over A, and then the other formula where the like the one, I don't get the difference between the two and like when to use which.
Okay. So let me come back. All right. So which formula are you asking about?
So like the relating load, life and reliability, where the like that really long formula to use, like the reliability contour is like over 90%.
Yep.
So
I'm almost there.
I don't get when to use that formula versus like the the shorter one where it's like the C10 equals AF times FB times XB.
Yeah. So either this one, or you can also use this one if you wanted to.
Yeah.
It's really just if you're going to change the reliability, that's when you use this version of the formula, basically. I have like one of the problems in the practice problem. It's also like a practice exam problem. There's also I think there's a problem out of the book. It's a little bit more conceptual. The really important thing is that for me, sometimes when writing an exam, that you actually understand what these things mean, and that you're not approaching it like I want to use which formula to use. So I'm really it's something that's important to me. I try not to be a jerk about it, but I also want to make sure that you're not in the mindset of I didn't know which formula to use. I hear that a lot after an exam, and
Mm-hmm.
I have to reply back to the person, well, that's some of the problem, because you were thinking like I don't know which formula to use, and I'm trying to make sure you're not a formula user, right? Like
Okay.
yes, you will use formulas, but you really got to try. I want to test, do you really understand what's going on, right? And I make the analogy, I'll make the defined point is like we're engineers and we're not technicians, right? So
Mm-hmm.
and nothing against the people who are a technology major, but they're very good, or they're learning how to put numbers into formulas, right? Whereas we have to think our way through the thing, and it's sometimes it's really pretty much the same thing, you know. But there is a certain amount where you can ask a question about something like this can really stump somebody because of the way that they were asked. So I'll give you a for instance by way of answering your question. Okay.
Okay.
So let's say now I know this is a question I've asked before, but I'm inventing this question here, and I'm going to say that a foreman has been going through the inventory of the machine shop, or maybe it's maybe it's a power plant and they have a lot of different equipment, and all of a sudden they find some bearings and they don't know what those bearings are, right?
Mm-hmm.
They're not labeled, but now all of a sudden they've got to try to almost do the same thing that the bearing manufacturer does and try to figure out what the rating of this thing is going to be. So they start using these bearings on some piece of equipment, and they don't really care all that much about the piece of equipment. So they can go ahead and like figure out how long it's going to last, right?
Yeah.
So we could just pick out a scenario, and we could say that like they went ahead and they tested this thing, and that bearing, they happened to know that they had like the application they guessed had an application factor of 2, right? It was pretty rough, but not as bad as they've seen. And the force that they were applying to the thing, they were able to measure it, and it turns out that it was 12 kilonewtons, right? And then they found it out that it was that it lasted like for 2 years, and it was running all the time at 100 RPM, right? So it was going all day for 2 years. These things fail. Okay, then now somebody says, well, hey, and they find out a bunch of them, and they said, well, that's pretty good. Okay, not so bad. And maybe that, you make it even more complicated. Maybe they found out that the reliability of this was 95%.
Mm-hmm.
So I've made it all kinds of complicated for myself, right? So what we could say instead of this is we could invent a new catalog rating for the thing, right? And say, well, let's make a catalog rating that's based on 90%, based on 1 million, right here, and based on an application factor of 1. That's essentially what we've done, right? We take that right here and we say this F times this thing. We figure out a ratio, this XD right here, and then we put all this other happiness inside it, right? All those, you know, and maybe we want to do it using the correct way right here. So let me write that down on my page, that XO plus right here. And we decided that they're going to go ahead and use the same method that manufacturer 2 used, the same Weibull parameters that they had. So what they've done now is they've created a catalog rating for these mysterious gears, right? So first off, our XD for these mysterious gears is going to be, let's see, it'll be 2 times 365 times 24 hours in a day times 100 RPM times 60, right?
Yeah.
And divided by 1 million. So that'll be my XD. So 365, 24, I forgot the 2, 100, 60, and then 1E6, boom. I have 105.1. So they said, and this was just a guess too, right? They said they were just guessing. They was like, yeah, that thing sounds like it's crushing marbles. So like, yeah. Okay. And we got all these parameters right here. Let's see if we could find these happy parameters.
And also the with the desired life, is it always going to be 1 million unless they say otherwise?
Yes. Yeah, unless they say otherwise. And
Okay.
and honestly, I probably, if I would, I was thinking of like totally mixing the thing up. Here we could maybe I could redo it just slightly without wasting too much of our time, and with another hypothetical. So, but let me get these values right here. So we had the XO is 0.02 and the theta was 4.459 and our B was 1.483.
Oh, and it also depends on which manufacturer it is. Okay.
Yeah, yes. But you also noted that with this one manufacturer, which I believe might be Timken, is 90 million as opposed to this one. It's 1 million. I think most everybody else does 1 million. And you go back to the reasoning behind that is it would take them a lot longer, the people with the 90 million, to like maybe test theirs or to be certain that they're testing theirs. And they might not even actually run it for 1 million cycles, right? They might do it for a particular number of cycles and then just use this same idea right here and then extrapolate up to get their catalog rating. They might do a bunch and then just massage it right there, because remember that the fundamental thing is that it's going to be right. That's like the concept right there. So whatever you do right here, like here's like what the test is, or let's say hypothetically that we run it for this and it fails for this. Well, let's do it instead. Let's change the time to this to see what this is going to be, right?
Okay.
So that's the long answer to your questions, like when to use which one, when to use the other one. It's really based on if you're going through a standard like kind of problem, and those are really just plug and chug kind of things. So I kind of try to not ask a completely plug and chug problem, but at the same time, I'm actually now, as I'm doing this, I'm trying to rethink and think that if I said this correctly. For my scenario, if he observed this right here, I gotta wonder if maybe I need to take this whole thing and put it up onto the numerator, because I want to turn this into 90. Okay, now I've got now I have to sit and scratch my head for just a little bit and have to triple check that I'm saying this the right way, because I could turn myself around here, and it's not good to try to do that live. It's an occupational hazard, though. Trying to decide. All right, so we use this equation right here when we want to modify their life, our expectations into their thing. And yeah. So I think what I said right here is I'd actually take this denominator, and for the application that he's showing right here, for this hypothetical, he is taking what he's observed to happen, and he wants to turn it into this rating life. Well, this rating life. No, we're good. I'm sorry. I'm going to take it back. Yeah. The big idea, what you want to try to use is, should this number be larger or smaller because of this, right? That now, if he observed 95% reliability, but he wants to have one that's 90% reliability, this will be a larger number than this. Does that make sense?
Oh, okay. Yeah,
Right?
that makes sense.
And since this always comes out to be a fraction, and we're dividing by a fraction, that will make this bigger, which will make this bigger.
Okay. Yeah. So yeah, that makes sense.
Yeah. So that's like the and in doing so and creating a problem like that, I have forced the student to try to go, what's really taking place here, right? What's the principle behind it? Because the biggest thing that I want to avoid is creating an engineer that's only capable of opening up a book and sticking and locating an equation and putting numbers inside it. Because you'll never find a book that contains every equation that you'll ever need.
Yeah.
And there's a lot of hazard. There'll be an equation that has all the variables that you have, and it equals the thing that you want to get to, but it's totally inappropriate for your situation. But I got to tell you, I've been as guilty as anyone in that mindset as an engineer, just hunting for an equation when you're not really sure how to approach the problem. So as I've grown as an instructor, I've recognized that in myself, and I've tried to kind of equip engineers to don't be like me, kids. Anyway, you get the idea with this.
Yeah, I do. I actually understand it better now.
Okay.
Thank you.
Yep. You want to go to another topic?
Yeah, pretty much the only thing that I didn't really understand prior to asking you is just the bearing part.
All right. Well, something that might be worth going through is some of the some of the problems that were from 370. And like I said, I don't necessarily ask those kinds of questions, but I might.
Okay. Is it just like 370 as a whole, or anything like specific?
Let's see. I just heard a bloop from thing. Quite often, if I okay, thanks a lot, Ref. If I was going to ask a question, it wouldn't be like something that was really hard, but it would be something like maybe a little bit more like, and I wouldn't want it to be like really time consuming. So a lot
Okay.
of times it might be something along the lines of the practice problems that I posted here. I
Okay.
I put in like, and this is like too long of a problem, but I might be like, calculate the von Mises stress at point K right here, but I might not make it a pressurized vessel.
Okay. Because I had 370 with somebody else, and we didn't
Yep.
like go through like that part in 370 either. So I just wanted to like make sure what I should like focus on more, because like some stuff like I didn't do in 370, but you taught um in your 370 class. So that's why I was just
Yeah,
I was just wondering.
yeah, well, see, that's some of the reason why I might ask a problem like this. Although this is unfortunately too long of a problem. Although I want everyone who gets out of my class just to have this skill set, right? To be able to,
Yeah.
if you needed to figure out the stress at point K, that you'd be able to
Mhm.
do it. Now we can simplify this, or we could get difficult into it. So I'm going to focus on this problem right here. Okay.
Okay.
Does that sound good?
Yeah.
Or okay, maybe not good. But
I mean,
anyway,
I don't, yeah.
let me write down the fundamentals of the problem onto my sheet right here. All right. Well, I can you can see these two, right? So they're posted right there. So
Okay.
I'll put this over onto my other screen if it'll let me. Okay. So I didn't make it a very pretty thing here. So we got this 450 millimeters to there. The forces, the dimensions there, come out to there, coming out to here is our Z. This right here is 240. And we have a force coming that way. We have a force coming this way. And we have a force coming this way. And we want to find it at this like side piece, this K. We want to find the von Mises stress right there. And that's 10 kilonewtons, and this is 14 kilonewtons, and this is 7 kilonewtons, and it's got a pressure inside it of 10 megapascals, and it's got a ID, well, I want to go OD first, right? OD of 95 millimeters and an ID of 85 millimeters. So we want to find the von Mises stress at K. Let's see right there. And I was kind of mean. I said, do not neglect transverse shear. So what we have to do here is, first of all, we have to figure out our loads, right? So every problem kind of has that type of thing. So our loads, what we want to do is have draw free body diagrams and make sure in our free body diagrams we don't put we don't put the ground in there, right?
Yeah.
So call it an FBD. This one I decided to go for Z and Y just because it was easier to look at it from this side because we were already kind of drawing it from that side. I'm going to look closely and see what the loads are that are on there. This is 10 kilonewtons. Right here is 7 kilonewtons. And you can't see the 14 kilonewtons here. So when you look at the reaction loads right here, we're going to have a reaction that's coming up and reaction that's going that direction. We're also going to have a moment reaction. So I don't know quite yet which direction this moment is going to go. That's right there at that spot.
Mm-hmm.
One second, me I got a hair on. I'm shedding left and right now lately. Um, okay, and let me as I'm on here, it's a good eye practice to like put on the dimensions. So this is 240. That's right in there.
I
And
actually thought I was balding at one point when I shedded a lot.
well, at the Merchant Marine Academy, they make us wear this thing called a garrison cap, which is kind of a pointy little hat. It's kind of it's long. You've probably seen them before, and but anyway, they kind of rub like right there, right where you know, the side of your hair, and so everyone thinks that that's making them go bald when we're in school. Like think that your widow's peak is getting your hair, your lines going back and forth. So let's see. This one is going to be. We could actually. I'll write the thing out, but we could say that the reaction. We could figure out the reactions just by observation. This is going to be 10 kilonewtons, and this is going to be 7 kilonewtons. But I went ahead and wrote them there. This guy right here, this moment, reaction moment. Notice that this one is going to create a clockwise moment, and this one goes counterclockwise. So we're not really quite sure. So when in doubt, this is the moment that's about the x-axis. We're going to pick this one to be, by default, make it counterclockwise, right?
Mm-hmm.
So I'm not going to bother with doing some of the forces because I can just, by observation, know that that one's going to be 10 kilonewtons and this one's going to be 7 kilonewtons. So
Yeah.
we take the moment there about the x-axis. I'll write down the reaction moment. No, this is a reaction moment. It's not this thing right here. And I drew it as positive, so he's positive right here. So I take that 10 kilonewtons, and he's going counterclockwise. So let's go 10. And this is kilonewtons in millimeters, so I can just, I know that I will get Newton meters out of it. So
Mm-hmm.
I'll go ahead and stay with the 450. And then this guy right here, he's going clockwise. And he's got a moment arm of 240. So I can find this one, and it turns out actually for this particular problem, by the way, I just noticed. Well, we'll say this in a minute. Okay, I'll hold off. So I could probably do this in my head, right? 450. That's 4,500. No, 4,500. Yeah, and then 7 times 240. Boom, and I subtract them out, and I end up finding actually that this is going to be a negative 2820 Newton meters. So I actually guessed it wrong.
Yeah, I got the same thing.
Yeah. So, but you know, it just occurred to me that like we're going to look at this point right here. This moment will cause a stress up here at the top, but won't do anything right here. Right. So this moment right here would cause a stress at H. But K is on the neutral axis, right? So this is a bending that's taking place about the X. So it's actually this moment right here. So it actually doesn't do anything at H. It doesn't do anything at K, excuse me, because K is on the neutral axis of the bending that would be caused by this. So we do need the other directions though. So like maybe we'll take a look at this direction, right? So I'm looking at it down this axis right here. And that will look like this right here, X. So most of the time I put the thing over to the side right here. And the forces that I will see from my problem, I'll see a force coming this way of 14 kilonewtons. And I will see a force coming this way of 10 kilonewtons. And so my reactions are going to be like that. And we know that's 10 kilonewtons, and we know this is 14 kilonewtons. But the moment that we see right here, we see this one's going counterclockwise. So this reaction, this M, we call it Z, because it's going about that Z axis, is going to be clockwise. So we said that negative mz, as we drew it out here, plus 14 times, and that's the 240 right there, right?
Yeah. Oh, okay.
So we get well, no, that looks like a 3,360 Newton meters. This one is going to be the thing that causes torque.
Mm-hmm.
And then the last one that we need to do, we need to look down on this thing. And so that's going to be the X direction here and the Z direction here. So maybe I like to put it over to the side. And the loads that we have on this are going to be 14 coming that way and 7 coming this way. So, and then in reactions, we should draw those on there. This is also 7 kilonewtons, and this is 14 kilonewtons. And the moment that's on here, we see that this one's going to go clockwise, so this one must go counterclockwise to and that's going to be the my, because it's about the y-axis right here, you know, about this axis. So we drew this as counterclockwise, and then this one is clockwise, so it's 14, and then this dimension right here, that was the 450. (14 times 450), and we get 6,300 Newton meters. Now this one is going to cause bending at K. But the question is whether will it be compression or tension?
Compression? Wait, no, tension. It'll be tension.
It'll be tension, right? Because you can think, as drawn right here, it's kind of going to be pulling on that because it's right here where K is. So that thing causes a pulling to take place on there. So
Yeah,
now
I just have to remember.
Now when we go stresses, we go down the list, right? Let's try with axial. Remember, that's going to be F over A.
Mm-hmm.
But then the question is, what force to use for axial? And the answer is, what do you think the answer is? I know it's mean to put you on the spot because you're the only student here, right?
No, it's okay. It's okay. I don't know.
Okay, it's the 7.
Okay.
Right, and it's going to be compression, right? Because you gotta picture what this thing looks like, what you know, almost like and when we're doing this, we're like cutting it right here onto the thing. So like we could almost like turn around and see from this side right here at the thing, it would look like this right here, right? So that we're looking at this little piece right here, and here's the little cube we're looking at K, right? So, but now I'm looking from this side right here onto the thing. And that 7 right there is a force that's like pushing kind of like in that direction. But not in the middle. It's compressing this piece.
Yeah.
Right here. And so it's going to be a 7,000. I like to turn them into kilonewtons when I'm going to do this. And for the area, I'm going to do it over to the side. Remember that this thing is hollow. So we're going to go pi over 4. And I'm going to take my outside diameter, 0.095 squared, minus my inside diameter, 0.085 squared. So I just don't want to mess around with millimeters and you know, in square millimeters. Millimeters squared just will confuse me. So I go ahead and make them really small numbers, and then just use the E notation onto the thing. I find that it just makes life just so much easier than trying to walk that line of remembering the conversion for the thing. So I got to multiply by pi and divide by 4. Did I do that already? I think I could take a look at it here. I think I get 1.414 E minus 3 meters squared. So I can look up here in a second.
I got the same thing.
So I get like 4.951 E6, and these would be pascals, right? And by the way, we want to make sure that we remind ourselves it's in compression. I could have put a negative right there. I decided not to, but I could put a negative in there if I wanted to. Which we know to be 4.951 megapascals, right? Look at that E6 right here. That's how I usually roll with the thing. Remind myself that's compression. Next I go bending. So maybe I'll write that's axial. You remember the equation for bending?
The
It's okay if you don't. I'm just gonna make sure that
I don't.
Okay.
I'm just trying to think if I do, but I don't.
Yeah, MC over I. It's a good one to memorize, right? It almost rolls off tongue. MC over I.
Okay.
The moment times the distance, this is going to be like, for us, it'll be like the radius, right? Because it's a circular thing.
Yeah.
It's the distance from the neutral axis to the outside fiber or at least the location that we care about, right? So it's the distance from the center. For us, it's going to be like from here to right there, right?
Yeah, I
So
remember. Yeah, I remember what C is. It's like it's basically like you said the radius D over 2.
I like to do these like over to the side instead of putting them into the middle. So we can, and to memorize the ones for a circular cross section, it's pi over 64 d fourthed, but you got to remember that this is hollow. So we have to do for 0.0954 minus 0.085 fourthed. And it comes out to really small numbers, right? Damn it. 0.09. Okay, and then 0.0854. And I subtract them out, and then I multiply by pi, and then divide by 64, and I get like 1.436 E minus 6. And so the moment that I use, we already decided that was the one that's causing bending. The distance to the outside fiber is 1/2 of the outside diameter. So I'll just write it as 0.095 divided by 2. And it's divided by that I. So 6,300.095 times, but then I have to divide by 2. And I get 2.084 E8. Those are pascals. And we already established that's going to cause tension. So that's 208.4 megapascals in tension. And now as I go down in my list of stresses, I have to remember this is a pressure vessel. So before I go to this, I need to have, there's 2 types of stresses due to pressure vessels. You remember them?
The hoop.
Hoop stress and longitudinal.
Okay.
We also call that transverse or tangential, whatever you. I think tangential. The book uses subscript T.
Okay. Wait, what chapter? Wait, what chapter is this on?
Chapter 3.
Okay.
And the big problem that we have to face when we do the hoop stress is we have to remember, is it going to be a thin-walled or a thick-walled vessel?
I remember. I remember that it had to like reach like a certain like number for it to be like a thin wall.
Exactly. Yep. And it's like what you want to find is you want to compare the thickness to the radius. I should have just opened this up right here. We come to this and we go to the stresses in pressurized cylinders. You know, you got to be careful in this section. If you're not familiar with it, you might start using all, you know, equations the wrong way. But this is the thick-walled equation for the tangential, aka the hoop stress.
Mm-hmm.
When there's only internal pressure, which is our case. Remember, here's something we do not have to find the radial right here. Just something to remember. Don't waste your time trying to find the radial. It's either going to be 0 if it's on the outside surface, or it's going to be equal to the pressure as compression if it's on the inside surface, right? So if they were asked to find the inside the inside stresses, that's what we would use. For this right here, this is the thing where it says it's 1/10 of its radius, right? So the thing to use to check out is first off, you want to figure out what the thickness of the thing is going to be, and that's like the people get this wrong all the time. Want to make sure that the thickness is going to be the OD minus the ID over 2. People always forget to do the 2 right there. So the thickness, so let's just do it in millimeters. 85 minus 95 is 10 divided by 2, so that we have a 5 millimeter thickness thing. The outside radius of this is just going to be 95 divided by 2. So we're left with 47.5. So if we were going to have, and then the inside radius, sometimes that's a good thing to get to. 85 divided by 2 is 42.5 millimeters. It doesn't really matter which one we use in this. We just want to double check the thickness divided by, let's use the outside radius. We get 5 divided by 47.5. So we get 0.105. So we're really, really close to deciding, should we use the outside radius or the inside radius? Well, it's kind of hard to decide. Let me see what I did for my solution. I'm curious.
At point K, wouldn't it make more sense because that point K is in the outside radius?
Well, no, not necessarily, because what we want to do, let's see. Okay, so no, we decided that this was thick. No, well, it's right on the border. We honestly, as a, when we acting as an engineer, we might want to say, well, let me try it out as both ways, but not during an exam, right? But if I was just doing it as an engineer, I would say, well, it's right there on the border of our 0.1. We said, we almost made it, right?
Mm-hmm.
But even if we did use the inside radius, right, we'd still would have been just just a little over there. We'd have 1.176. So we have to make this. We decide that we need to use the thick-walled equation, which is annoying because it's a longer equation to use.
Mm-hmm.
But we go ahead and write it down. We're engineers. We know how to survive adversity here. So the thing we wanted for this is it's the pressure times the inside radius squared divided by the outside radius squared minus the inside radius squared times 1 plus the outside radius squared divided by r squared. Now, r is the location where we're checking. We happen to be checking on the outside, right? Because that is where we're located, right? At K, which is on the outside surface. So actually, this R is equal to the outside. So we could actually just look at that. It's going to be, that's just going to make this 1 plus 1. So that's just going to be 2. We could actually skip a little bit of step right there. So we could also, we know that it's going to be 10 megapascal times the inside radius, which is, and by the way, this is going to be radius down here, and this is going to be radius squared up here. So these are actually going to cancel out. So we don't actually have to use millimeters here, right? This is just good. All the units will cancel out. So we could maybe take a little bit of a shortcut. We could even use the diameter if we wanted to by the thing, because that would also would cancel out. But we'll take our 42.5 squared divided by my outside of 47.5 squared minus my inside 42.5 squared. And remember that we're multiplying it by 2 only because this is the location of the thing, so that equals 2 right there. So let me come back down to here, and we're gonna get megapascals as our answer for here because we're using megapascals here. So if I do all of that, I end up with an 80.28 megapascals. And hoop is always going to be in tension because it is the kind of stress that's trying to make this thing bigger, right? It's a pushing outwards of the thing, and hoop is going to be the stress that kind of goes in that direction. We think of it as a tangential stress because it's just like you're inside of a hula hoop. I always think of that. And you're trying to push your way out, you would be stretching that hula hoop, right?
Yeah. Okay.
So that's the kind of stress that we're dealing with. So that is in tension as well. And it turns out the longitudinal one is really much all the same stuff. So if we go and take a look at the longitudinal equation for longitudinal stress, whoops, let's see, right in here. We see this, we compare that one to this one. We'll see that the longitudinal is really just that part right there.
Yeah. It's just the first part of it.
So it ends up just being 1/2 of the hoop stress.
So 40.41 megapascals.
Yeah. And it too is in tension because it's the one that's trying to stretch and make this thing longer, right? It's kind of the idea that like it's along the long axis is trying to push and make the thing longer. So it too is in tension. Now we also want to get now those are all the normal stresses. Now we need the shear stresses. So we have torsion. And like the bending one, I won't put you on the spot. This is a good one to memorize because it's similar. TR over J. And J for a circular section is just 2 times I. So what we're left with is, I think I do it up here, up above. I say that it's 2.872. And these are meters fourth, not millimeters fourth, meters fourth. I forgot to write on there. And the torsion, as we said up above, was going to be 3,360. And the radius of this, we already have that. We used it up here, right there. We could have actually just used up this guy right here, right? We could have just written out at 0.0475 divided by our 2.872 E minus 6. We do all of that, and I actually have it written down somewhere. It's 5.558 E7. So our 55.58 megapascal. And that's not tension or compression. I have to be careful of that, right? Because it's a torsional shear. It's a shearing type of stress that's on the stress element. And then the last one is sort of like this one that we will often forget to include. A lot of times it's neglected. It's transverse stress, transverse shear. And it's kind of similar to the idea of direct shear, which is like the shear that's due to scissors, right? Where you're trying to cut something, so you're trying to slice it. So it's going to be the force that's trying to slice down across the face of the thing. And there's really two to choose from. We either have this one in this direction, that 14, or that 10. And we have to decide which one is going to cause that transverse shear. The best way, I think, well, there's several different ways, but maybe to try to remember this, but this is also called, by the way, it's also called beam shear. So the shear stresses in beams is where this is brought up. Instead of going to first principles, well, I don't even know if you call them first principles. Instead of trying to do a generic equation, we can go ahead and look up in a table what we want to use for this. And so I think the approach that I prefer to use is just to remember that I want to look this up for a particular shape, and then I want to look at that figure, and I can see that for a force that would be going downwards. I don't have my pen on this. I don't know why I don't have a pen on here, but anyway, if I were to put a comment on there, can I go with a comment? Here, here's a pen. Okay. So all of these figures are for a force that's going downwards, right? So the shear they're referring to is downwards. So it's actually to the side where we can find out that we have a maximum shear stress that's taking place. So a stress element that's just to the side right here has the maximum amount, and up here actually where it's passing through is actually 0. So for our transverse shear, we can use that equation and say our trans is equal to 2 V over A, because this is a hollow cylinder. And the V that we use here, by V I mean the force that's coming down, the shearing force. If we look down on here, it's the 10 that's coming downwards that will cause, this thing will be to the side of the 10. Whereas as the 14 is coming out this way and passing through this. So the 14 does not cause transverse shear to K. It causes transverse shear to H. But this 10 is the one that's causing transverse shear to K. And good idea to use the kilonewtons thing. And we already have the area here. So 1.414 E minus 3. And what we're left with, I'm cheating and looking at the answer here, if I can find my mouse. We're looking at K. We get that it's going to be, it's something pretty small. No, actually, I think it turns out to be significant. Yeah. I'm just going to write it down as megapascal. Now here is one of the most important, but I want to say stressful, but one of the most stressful aspects here is to try to add these things up together. So what I like to do is draw like a little cube that's oriented similar to what I have right up here. All right, so first off, let me put in my axial right here. That was compression. But then I had bending. That was tension. I also had longitudinal. And longitudinal is trying to make it longer, right?
Mm-hmm.
So it's going in this direction. But hoop is trying to make it expand out in this direction. So it comes out in that direction. This is a tough thing that students really struggle with. Right? By the way, my orientation is like this right here. So I might even want to draw it like here. Here's my Z, here's my X, and here's my Y. All right, so that wasn't too bad, but the bad thing is when people like will mix this up and put them in there. Another way to draw it is to look at this face right here, and we're going to say here is our bending plus our longitudinal minus our axial in this case, because this is in compression.
Mm-hmm.
And then up in this direction, we're going to have our, I wrote T, but because that's the way they had in the book, but I could write hoop as well. And now our next stress, we're going to have to do shear. And so this one's a little more difficult. You got to picture the direction that this thing is causing shear, right? So it depends on which side of the piece that we're looking at. And I often tell people that I like to, instead of looking at the free body diagram, I like to look at the stump, right? So I cut the thing off, but I want to see what's happening to the stump. And so this guy right here is causing a shearing action on this face in that direction, which is opposite from what the reaction that we got right here was down this way. So this guy is the reaction face. This is from the free body diagram, where this guy right here, that's the stump. Right, so this 14 is causing a twist onto this direction right here. So that means on this side of the thing, this is going to be a shear, I want to say this the right way, that's coming up the face. Right there. So,
okay.
so this is the torque. Now, similarly, this 10 is coming down the face that way right there. So it creates a transverse shear in that direction. So our conclusion is they're opposite from each other. I know. It's a really this is a really difficult thing to, for students to master, right? So as looking at this element right here, we have that guy right there is our torque, and that on this onto this face is our trans. So if we're going to work out these, the actual numbers right here, and this is, once again, this is the Z direction. This is the Y direction. So we'd say that the normal stresses in the Z direction are going to be, bending is 208.4, longitudinal is 80.28, and axial is 4.951. And remember that it's negative.
Yeah.
Oh, wait a minute. Did I get that wrong?
What did you get for the
I think this should have been
axial?
I think this should have been 40.
Yeah, it was like 40 point. No, the longitudinal was supposed to be 40.14.
Yeah. I was looking over here because I had accidentally tried to cram everything back into place. So I get for K 243.6. And in the Y direction, it just equals the hoop. So this is 80.28. And for shear, which we would call technically the ZY or the YZ, depending on how you say it. Like most of the time, the convention is this is the face and this, whoops, I'm not pointing to it. This is the face and this is the direction. So this, we could consider this the Z face, and then this is the Z face because it's perpendicular to Z, and this is the Y direction. So this would be the ZY face right here. And upwards, well, it doesn't really matter. We'll say that, but the upwards right here is going to be, this ends up being larger, right? That the torsional shear that we found was 55.58. And the transverse was 14.15. So that ends up 41.43 megapascals. And that would be going up. So if we're going to summarize on yet another stress element, stressy, the stress element. Oh, I should have left myself some more room. I would say that we only have to draw it once onto there. This would be my 243.6. This would be my 80.28. We looked over on this face and found that there was the torsion that going up. So this is the direction that that would go. All the others point this way, right? We have to remember when we draw this out, the thing has to balance out. So these will point towards each other. And this side will be the opposite of that one. This one will be the opposite of that one. And I like to write it up here in the upper right-hand corner, 41.43. And then when we go to von Mises, remember though, we will be tempted to use that for von Mises, but that's only for the condition when we have uniaxial stress. Right, this equation is for that. We need to use the one that's longer. I'll write it over here. I'm writing X, but it could be either one. I'll write it right here. So I'll say Z squared minus sigma Z sigma Y plus sigma squared plus 3 tau. In this case, it's a ZY squared. So 243.6 squared minus 243.6, 80.28 plus, not going to fit it in there. I might get it. And let's see, for K, 226.7 megapascal. That's a really long problem.
Yeah.
I can't ask that problem on an exam, but I can ask a part of one. I don't know. But I did think it's important for anyone that didn't take me in 370 to have, maybe this hopefully be refresher to get the big idea of a really complicated problem.
Yeah, because like the problems that we would get in my professor did would be like a part of it, like very very simple, like a much simpler version,
Yep.
pretty much. And it's just like I don't know, that class was like more of just like using the formula and plugging it in. It was like very like formula based, where like
Yeah, I'm trying
and
to
like
make it
I
a little
didn't.
bit more, trying to keep it a little more conceptual, because I think
Yeah,
the conceptual stuff is going to last longer than the
yeah, it really does.
situational specific approaches.
Yeah, I noticed that
So
too. I was
look
like,
at another problem. Let's if you have the time.
uh,
You're getting the
yeah, I
one.
was
You're getting the
sometimes.
one-on-one treatment here, and we're everyone back home is watching this video. No, that's not. That's probably not. I'm wearing my flannel today. Look at that. See, you can see my flannel.
Nice day out.
Okay, so. Oh yeah, I should go outside, shouldn't I? I didn't drive to work. That means I should have 2 extra hours today. Although we're losing some time coming up this Sunday. It's
Oh yeah, isn't it the daylight savings is over?
yeah. You know
Wait,
what?
aren't we gaining more sunlight?
I try not to have any real strong political beliefs, but I'm going to go ahead and come out strong. I don't like daylight savings time. I don't like it.
Wasn't it mainly used for like the like in the war so that they like turned the lights off earlier?
I think maybe I might have heard something on those lines. I used to think it was because of farmers. I don't know. I don't know why that doesn't make a lot of sense. But also somebody did say that decided that they could save more energy somehow. They did some kind of math about like I don't know.
Oh, it said that it was to like save energy and stuff like that for like the during World War One, but then after the war it stopped, and then they started doing it again and never stopped since World War Two.
Well, I just think there's some places that just refuse to do it. There's like I think Arizona doesn't do it.
Yeah, Arizona. I don't think
In
Arizona
Hawaii,
does it. Um, hmm. the
I'm totally okay with that.
Do you know about graduate school? Do you know a like industrial or like product design like like masters?
It's kind of hard to say. Like most of the time, graduate stuff, unfortunately, graduate school is less and less about the practical and more about the theoretical.
Really?
Yeah, graduate school, but at the same time, industrial engineering is probably a field, but also that industrial engineering is kind of closer to being more of a management degree.
No, I wanted it's industrial design.
Okay, industrial design. I don't
Yeah,
know.
it's so like instead of like so
By the
instead
way,
of
this is
like
being
doing like
recorded. Remember.
okay.
figured I'd tell you. And I'm totally okay with talking about it. I just figured you'd want to, we could talk about it afterwards. If you want to, we got another 15 minutes
Okay,
maybe
yeah.
of more problems, or
Okay, yeah,
if
that's
you don't
fine.
have any more questions, we can kill it now. That's fine with me.
I'll just wait till after.
Okay. Yeah. So what kind of problem would you like to do? We want to do a gear stress problem?
No, I'm actually fine with all the gear stuff.
Okay.
The gear stuff is like probably like the I wouldn't say the only thing, but like the thing that I'm like actually enjoying and like understanding.
Okay.
Yeah. Um,
Are you okay with gear forces? I've seen people that
gear
struggle with the gear, getting the directions right on the gear forces.
at first I had I had trouble with it, and then like you did like an example thing for like the forces when you did for class 11 when we were doing the rolling bearings and you were doing the free body diagram for the um thing. That's when I was like, oh, okay, now I understand it
Okay,
better.
good. Yep.
Yeah. And I also looked at the homework solutions, and I understood it a little bit better on there too.
Okay, good.
So yeah, I'm pretty much like set at this point.
Okay, well, cool. So there ends the review session. I hope those at home that I hope you can get something out of it. There's also a recording from previous last year, I think. I think that could be helpful to other students. And